In this module, we shall learn the difference between means and proportions in hypothesis testing. The theory behind testing the difference between two means is based on selecting pairs of samples and comparing the means of these pairs. The population means need to be known. All possible pairs of the samples are taken from the population. The means for each pair of the samples are computed and the differences are plotted.
After studying this module, you shall be able to understand the concept of sampling distribution of the difference between means, to learn to apply the concept of difference between proportions. Let us begin by understanding the assumptions of difference between means. The difference between means is based on the following assumptions. First, the samples must be independent of each other. That is, there can be no relationship between the subjects in each sample. The sample chosen from the population is designed according to the study. Second, the populations from which the samples were obtained must be normally distributed, and the standard deviations of the variable must be known, or the sample sizes must be greater than or equal to 30. All possible pairs of sample are taken from population. The means for each pair of sample are computed and then subtracted, and the difference are plotted. If both populations have the same mean, then most of the difference will be zero or close to zero. Occasionally, there will be a few large difference due to chance alone, some positive and others negative. Now, moving on to the method for computing the sampling distribution of the difference between means. As you must be familiar with the sampling distribution of the mean, we use another theoretical sampling distribution, the sampling distribution of the difference between means, to test hypotheses about the difference between two sample means. The standard error for the difference of two means is based on two independent random samples, that is, observations in population 1 are not affected by observations in population 2, and vice versa. The sampling distribution of the difference between sample means has a mean mu1 minus mu2. The proper approach depends on the sizes of the samples n1 and n2. If both n1 and n2 are large, that is at least 30, the technique differs somewhat from that when either or both sample sizes are less than 30. The standard deviation or the standard error is given as follows: sigma y1 bar minus y2 bar is equal to under root of sigma y1 square upon n1 plus sigma y2 square upon n2. In this formula, n1 and n2 are the sample sizes of the two samples, and sigma y square are the variance of the two samples, namely y1 and y2, from which the sampling distribution of the difference between means is calculated. The sampling distribution is approximately normal under the central limit theorem. The formula assumes that we know the population variances, and we can use the population variance to calculate the standard error. However, we are usually using sample data and do not know the population variances. When we use sample variances instead, we end up getting an estimate of the population variance, not its true value. This situation automatically makes the normal distribution inappropriate for testing purposes. Secondly, this estimate can be obtained through two different assumptions. When we can assume that the population variances are equal, we use the formula to calculate the standard error. In other words, when the two population variances are equal, then there is some variance sigma square common to both populations. That is, sigma 1 square is equal to sigma 2 square is equal to sigma square. However, due to sampling error, if a sample is taken from each population, the two sample variances will likely differ from each other, as well as from the common variance sigma square. But since the populations have a common variance, the data from both samples can be pooled to obtain a single estimate of sigma square. This is done by computing the weighted average of the two sample variances, where the weights are the degrees of freedom n-1 for each sample. Since the two samples have different sizes, we rely on larger sample and take a weighted mean, which is given as S y1 bar minus y2 bar is equal to under root of n1 minus 1 into S y1 square plus n2 minus 1 into S y2 square upon n1 plus n2 minus 2 into under root of n1 plus n2 upon n1 into n2, where S is the sample standard error. This formula gives us the pooled estimate of the variance. Pooling generates a weighted average as the estimate of the variance, where the weights are the sample sizes for each sample. A pooled estimate is thought to be a better estimate if we assume that the variances are equal. If either sample is small, that is less than 30, we cannot assume that the distribution of the difference in sample means, that is y1 bar minus y2 bar, fits a normal distribution. The normal deviate z therefore cannot be used. Instead, when the populations are normally or near normally distributed and the population variances are unknown, then we must turn to T-distribution. To apply T-distribution properly, we must also determine whether the variances of the two populations are equal. We use the T-distribution and the T-statistic for hypothesis testing for the differences between two sample means. The formula for the obtained T for a difference between means test is T is equal to y1 bar minus y2 bar upon standard error S y1 bar minus y2 bar. We also need to calculate the degrees of freedom for the difference between sample means. When we assume that the population variances are equal, or when both sample sizes are greater than 30, we use the following formula. Degrees of freedom df is equal to n1 plus n2 minus 2. The degrees of freedom becomes larger in case of a pooled estimate of the variance. Thus, our t value becomes smaller in such a case. The rejection region for a level of significance alpha is given by t greater than equal to t star alpha for right-tailed test, t less than equal to T star alpha for left-tailed test, and either T greater than equal to T star alpha by 2 or T less than equal to minus T star alpha by 2 for two-tailed test. If the population variances are unequal or there is no evidence to assume an equality, the procedures described above do not apply directly, because the distribution of differences between sample means does not fit a t-distribution with n1 plus n2 minus 2 degrees of freedom. In fact, no exact distribution has been found to adequately describe the sampling process, and only approximation have been developed. One such approximation has been proposed using the T-statistic with degrees of freedom slightly altered. If the population variances are not assumed to be equal, the separate sample variances are used as an estimate of sigma x1 bar minus x2 bar. Sigma x1 bar minus x2 bar is equal to s1 square upon n1 plus s2 square upon n2 whole to the power 0.5. In this more complicated case, the degrees of freedom is given by df is equal to s1 square divided by n1 plus s2 square divided by n2 whole divided by s1 square upon n1 divided by n1 minus 1 plus s2 square upon n2 whole divided by n2 minus 1, where s1 square and s2 square are sample variances. We can illustrate this concept using an example. A study was conducted to examine whether right or left-handedness affect how fast people type. Random samples of students from a typing class are given a typing speed test, words per minute, and the results are compared. Significance level for the test is 0.1. Since you are looking for a difference between the groups in either direction, that is, right-handed faster than left, or vice versa, this is a two-tailed test. Here, the statistics of the sample are given in the table as shown. Here, n is the number of observation in each group and s is the variance for each group, that is right-handed and left-handed. The mean of the right-handed group is 55.8 and that of left-handed group is 59.3. Here we have null and alternative hypothesis as null hypothesis H naught is equal to mu1 is equal to mu2, or H naught mu1 minus mu2 is equal to 0. Alternative hypothesis HA mu1 not equal to mu2, or HA mu1 minus mu2 not equal to 0. First, calculate the pooled variance. SP square is equal to 16 minus 1 into 5.7 square plus 9 minus 1 into 4.3 square whole divided by 16 plus 9 minus 2, which is equal to 487.35 plus 147.92 whole divided by 23, which is equal to 27.62. Next, calculate the t value. T is equal to 55.8 minus 59.3 minus 0 upon under root of 27.62 into 1 upon 16 plus 1 upon 9, which is equal to minus 1.598. The degrees of freedom parameter is 16 plus 9 minus 2 or 23. This test is a two-tailed one. So you divide the alpha level, that is 0.1, by 2. Next, you look up T 0.0523 in the table, which gives a critical value of 1.714. Since this value is larger than the absolute value of the computed T of minus 1.598, so the null hypothesis of equal population means cannot be rejected. There is no evidence that right or left-handedness has any effect on typing speed. Let us now look at the limitations of this model. First, this concept may result in a spurious result. Suppose there is a study on the cause of death of Delhi University teachers. The researcher takes a sample of 100 teachers. It was observed that out of 100 teachers, 20 teachers who wrote their biography lived longer than the other teachers. When the above formula was applied, it was found that the difference of means was significant, which implies that not writing biography results in early death. This is an illogical reasoning behind the death of Delhi University teachers. Therefore, it results in spurious results. Further, we will discuss the assumptions of the sampling distribution of difference between proportions. It is based on the following assumptions. First, the sampling method for each population is simple random sampling. Second, the samples are independent. Third, each sample includes at least 10 successes and 10 failures. Some texts say that 5 successes and 5 failures are enough. And last, each population is at least 10 times as big as its sample. The theory behind testing the difference between two proportions is to test whether they are significant or not. Problems often arise in the business world requiring the comparison of two different population proportions. The proportion of defects produced by one method compared to that produced by a second, or the proportion of bad debts in one firm compared to that in another. As learned in the previous section, in a similar manner, we will understand the method for testing the difference between proportions. Next, moving on to the sampling distribution of difference between proportions. pooled sample proportion. Since the null hypothesis states that P1 is equal to P2, we use a pooled sample proportion P to compute the standard error of the sampling distribution. P is equal to P1 into N1 plus P2 into N2 divided by N1 plus N2, where P1 is the sample proportion from population 1, P2 is the sample proportion from population 2, N1 is the size of sample 1, and N2 is the size of sample 2. Next is how to compute the standard error of the sampling distribution difference between two proportions. Standard error is equal to square root of P1 into 1 minus P into 1 divided by N1 plus 1 divided by N2, where P is the pooled sample proportion, N1 is the size of sample 1, and N2 is the size of sample 2. Test statistic. The test statistic is a z-score defined by the following equation. Z is equal to P1 minus P2 upon standard error, where P1 is the proportion from sample 1, P2 is the proportion from sample 2, and SE is the standard error of the sampling distribution. The analysis described above is a two-proportion Z test. We can further understand this concept with the help of an example. In a study of patients on sodium-restricted diets, 55 patients with hypertension were studied. Among these, 24 were on sodium-restricted diets. Of 149 patients without hypertension, 36 were on sodium-restricted diets. We would like to know if we can conclude that in the sampled population, the proportion of patients on sodium-restricted diets is higher among patients with hypertension than among patients without hypertension. The data is given in the table. Here, the number of patients with hypertension is 55 and that without hypertension is 149. The sample proportion of patient with hypertension is 0.4364 and that of patients without hypertension is 0.2416. The assumption on which it is based is that there are independent random samples from the populations. Moving on to the hypothesis, we have H0 P1 less than P2, H1 P1 greater than P2, and the test statistic Z is calculated as Z is equal to P1 hat minus P2 hat minus P1 minus P2 naught upon under root of P bar into 1 minus P bar upon N1 plus P bar into 1 minus P bar upon N2. Next is the distribution of test statistic. If the null hypothesis is true, the test statistic approximately follows the standard normal distribution. The decision rule states that with alpha is equal to 0.05, the critical z-score is 1.645. We reject if z is greater than 1.645. Moving on to the calculation of T-statistic. Z, which is equal to P1 hat minus P2 hat minus P1 minus P2 naught upon under root of P bar into 1 minus P bar upon N1 plus P bar into 1 minus P bar upon N2, which is equal to 0.4364 minus 0.2614 minus 0 upon under root of 0.2491 into 0.7059 divided by 55 plus 0.2491 into 0.7059 divided by 149, which is equal to 2.71. Moving on, how to make the statistical decision. Reject H naught because 2.71 is greater than 1.645, and thus we can conclude that the proportion of patients on sodium restricted diets among hypertensive patients is higher than in non-hypertensive patients. Further, moving on to understand the need for difference of means test. The difference of means test is used when we have two independent random samples. The next step is to determine whether we are dealing with a mean or proportion. If we are dealing with a mean, we next need to look whether we have small samples or large samples. If we have large samples, then we do not have to assume anything about the distribution of the population or anything about the variances. We can calculate standard error and conduct testing using a Z value. But if we have small samples, then we must assume that they are independent random samples. The next assumption is that both the samples are from populations that are normally distributed. And the last assumption is that their variances should be equal. We will then calculate the pooled estimate of the variance. Using this pooled estimate to calculate the standard error, and finally conduct the test using a t-value with n1 plus n2 minus 2 degrees of freedom. Now, moving to the need for difference in proportions. The difference in proportions is based on large samples only. It uses the same strategy as in case of mean. We calculate the difference in the two sample proportions and establish the sampling distribution for our estimator. The next step is to calculate the standard error of this sampling distribution and finally
Let us now summarize what we have learnt in this module. The concept of difference between two means is based on selecting pairs of samples and comparing the means of these two pairs. Secondly, the difference of means test is used when we have two independent random samples. Thirdly, when we are dealing with a mean, we next need to look at whether we have a small sample or a large sample. If we have large samples, then we do not have to assume anything about the underlying distribution of the population or anything about the variances. When we have a small sample, then we have to assume that both the samples are from populations that are normally distributed and their variances should be equal. 6. When we calculate the pooled estimate of the variance, we use the pooled estimate to calculate the standard error. And finally, when we conduct the test using a t value which has the n equal to n1 plus n2 minus 2, which is subtracted for the loss of degrees of freedom. This could also result in spurious results, and it is important to take the necessary precautions. Then we have learned to apply the concept of difference of proportions with the help of two proportions Z test. This is in the case of large samples. The difference of proportions is based on large samples and is akin to the difference in means, but there are certain crucial differences.